My name is Shankar, and I manage the Powertrain controls team in Southwest Research, and I'm joined here with my colleague Stas Gankov. And this talk will last probably about 40 minutes. And the question or the focus of the discussion here is how traffic simulation and applications and how they are being relevant to a powertrain engineering perspective. So here's a quick outline of the talk today. So I don't know how many of you are actually familiar with Southwest, so we just wanted to quickly introduce who we are, then talk about this concept called connected powertrain that we have been working on for the past 3 or 4 years at Southwest, and then we will bring in the role of traffic simulation and what are the objectives, why do we really need a traffic simulator, and then we will talk about specifically on how we are leveraging tools such as PTV Vissim and how we are building the environment for vehicle testing and powertrain application. And then we will talk about some of the efficiency and energy perspectives and benefits of the technology that we have been working on. And then we will summarize with some conclusions towards the end. So a very brief introduction to Southwest for people who are not familiar. So we were established in 1947 by Thomas Lick Jr. We are a 501c3 nonprofit corporation. We are headquartered in San Antonio, Texas. So over here is the aerial view of the institute in San Antonio. So we are about a mid-size company, around 2,800 to 3,000 employees, pretty large facility and heavy capital intensive facilities, like about a 1,500 acre facility, 2.3 million square feet of labs. And we are an applied R&D service provider, so 10 technical divisions spanning the technologies all the way from powertrain to space applications. For example, the recent Juno mission was the PI was from Southwest. Then we have a division for automation and connectivity based vehicles, then mechanical engineering, and so on. And very R&D focused, so a lot of patents and trade secrets and IP in general. Revenue in 2019 is about $675 million. So that's who we are. And where both we and Stas come from, where we are from the powertrain engineering division. We do everything from your lawnmower engine to locomotive and marine engines. A big focus towards electrification in the recent areas, but we span around the whole spectrum in terms of powertrain applications, after treatment, as well as transmission technology. As automotive engineers and powertrain engineers, one of the key things is that we have spent a good amount of the last decades and spent significant amount of resources and dollar essentially on improving fundamentally the machine that transports us from point A to point B, be it people or be it goods. And here is the Environmental Protection Agency, EPA, their historical data on how we have fared in the past 4 or 5 decades in terms of fuel economy and CO2 emissions. And as you can see, around the model year 2018, from a fleet real world fuel economy standpoint, we are roughly at about 25 miles per gallon for model year 2018. And the CO2 number is at about 353 grams per mile. As the mobility as a service revolution and connected and automated vehicle revolution started happening in the last decade, one of the questions that we wanted to answer is, yes, in the recent past years, like powertrain or automotive centric efficiency improvements are pretty much incremental in nature, like 1%, 2%. And what we want to understand or answer the question is, can we leverage data enabled through connectivity and automation and write software on top of it to now not go after incremental changes in efficiency, but achieve leapfrog levels of improvement, such as 20%. And can this be achieved via connectivity and automation? So the question is, can connectivity overlaid with simple vehicle automation lead to significant energy efficiency benefits? So the world around us is getting connected in all sorts of ways. And when I talk about connectivity, I think I wanted to kind of focus a bit on what exactly do we mean by that. And there is one kind of connectivity, which is just the regular 4G LTE systems that you have in your vehicles these days. Like, it kind of powers the infotainment. You're able to go look at Instagram or put TikTok videos and see things like that. And then there's another breed of connectivity, which is what we are talking about as the short-range communication enabled via two technologies that are kind of gaining some kind of being debated in the intelligent systems world, which is dedicated short-range communication platform, which is DSRC, and the other one is the cellular V2X or the CV2X umbrella under the 5G spectrum. But broadly, everything classifies under the V2X category, and primarily what we are leveraging for this application, at least, is V2V, which is vehicle-to-vehicle, and vehicle-to-infrastructure applications. So the next question we wanted to answer is, okay, automation, where are we? I mean, pure L4 technology, it's still some time out there. And what exists in the world right now, where I can just go buy a car, is L2. I can buy a level 2 vehicle that has the regular radar assist cruise control, our standard lane keeping assist, and things like that. And the question, what we are trying to see is, even simple levels of automation, what kind of impact do they have? And here is a simple experiment, but really nice experiment, which was conducted by these universities. And what the goal here is, all the drivers form around a big circle, and they have to drive at a constant speed. As you can see, the initial run is okay, and what starts to happen around the 80-second mark over here is something we are all very familiar in our traffic, in our day-to-day drive every day. And here are some metrics that were tracked. So in throughput, what are the number of braking events? How did we do in fuel consumption? And what is the deviation of speed of vehicles around us? And what happened is, at around this mark, this vehicle alone, we engaged something as simple as cruise control, but the researchers engaged something as simple as cruise control. And now let's see what starts to happen. And initially, things look starting to get stable. Keep in mind, all the other vehicles are still driven by regular, normal human drivers. And what starts to happen is something very interesting, that this one vehicle, which has technology like cruise control, not only is its speed becoming steady, it is also starting to affect the speed and fuel and throughput, the braking events of all vehicles around it. And it has this effect of affecting the neighboring traffic around it. And this is something that is a very key takeaway from this experiment. So even simple automation, it does not have to have penetration of technology across all the vehicles around it. Even a few vehicles in the traffic environment can have a significant effect of improving performance of vehicles around us. So how we define the umbrella of connected powertrain is, here is our intelligent systems world, which works on things like vehicle connectivity, traffic flow modeling. They build the automated vehicles, do the perception, localization, also do the cloud computing, big data. But be it a human-driven vehicle or an automated vehicle, effectively it survives in this environment and translates basically through choosing a speed or a decision, it translates it into a power demand. And then the powertrain engineering folks come into action. And what we do is we say, okay, here is what my user wants, and I'm going to actuate exercise the different actuators on my powertrain to deliver the power demand that the user needs. And where connected powertrain comes in is right in the middle. So step one, what we want to do is we want to leverage data and help the user minimize power demand by making him or her smarter driving choices. And the second one is we want, now that we have minimized or optimized this power demand, now we want to go extract it in the most efficient manner from our powertrain. So the one-line objective is leverage connected and automated information streams to improve energy efficiency and performance of the powertrain. With that background, so we started a program called NEXTCAR. It stands for Next Generation Energy Technologies for Connected and Automated On-Road Vehicles. And it was a 3-year program. It was funded by the Advanced Research Project Agency under the Department of Energy, ending in fall 2020. And our partners on this program were Toyota and University of Michigan. And applying concepts of connected powertrain, we demonstrated energy consumption reduction of 20% over a Toyota Prius Prime. And this is a plug-in hybrid. And if achieving the 20% target was not challenging enough, one of the key requirements for the program was we shall not make any powertrain hardware changes. And also, we cannot affect the emissions, the safety, or the drivability aspect of the vehicle in any fashion. So in short, all the energy consumption benefits need to be obtained in purely through software and data. So the way the technology was structured is kind of at 2 layers. One, we kind of define it as the energy layer. So think about the macroscopic level of whole route information. So we are leveraging standard connectivity. So we have coarse information about whole route. We are taking into account things like traffic congestion, what is my elevation across the route, stop signs, school zones, where are my charging opportunities, etc. And effectively, the first thing is choosing an energy efficient route that is specific to your powertrain. And we will cover some of the details later, but the idea being that just always take the fastest route is not the best route in terms of energy. And also, you cannot take too much of a penalty in terms of trip time just to make sure that you're saving energy. So there is a compromise, and we kind of address it. And the second one is kind of a more specific to a powertrain itself. In this case, for example, we have our the plug-in hybrid, which has a battery pack as well as an engine. Now we are able to leverage this information and say, how do you better plan where my engine should engage, where should my battery or electric machines engage, and high-level planning like this. The second layer is kind of more focusing on a mesoscopic scale. So about a 500-meter radius, so think about it as a DSRC radio's range, roughly half a kilometer. And what we have here is shorter horizon, but much finer resolution information. And we leverage the onboard sensing information, for example, things like your radar, your camera, all that gets fused into this layer, along with information about V2V and V2I. And what effectively we are doing in this level is understanding what's the best way to drive or help the driver make smarter driving decisions by minimizing unnecessary acceleration, braking, and also key is like, don't affect the traffic significantly around you as well. So just don't drive really slow just to save on energy. So it takes all of that into account. And then here is a summary of the benefits on how our stack up towards 20% was. And you talk about eco routing, which is the energy efficient routing, roughly about 3%. The power split planning was what we mentioned about the optimized operation between your engine and electric machines. And the acceleration smoothing and eco A&D talked about eco approach and departure towards signalized intersection. And acceleration smoothing basically refers to things like knowing the vehicle or traffic around you and now optimizing your driving trajectory to save on energy. So what we will focus on this talk really is more about the bottom portion of this pie here, which is where the traffic simulation and that kind of application becomes very relevant. One of the other things we are doing, and this is a follow-on program, is we are currently engaging with the Department of Energy on a program, and on the side are highlighted some of our partners on understanding the impact of not just one powertrain, right? How do concepts like these affect different kinds of vehicles with different powertrains, different levels of automation? If you have level 0 and going all the way up to level 4, as well as understanding the impact of things like intelligent infrastructure. How can we attain system level benefits via technologies like this? And with that, I'm going to let my colleague Stas, who will now go into details on how exactly are we leveraging traffic simulation and using it for testing the powertrain.
Thank you, Sankar. So first I will discuss the objectives of using a traffic simulator. Now, Sankar kind of introduced the overarching theme of us doing lots of different testing and being able to test out various technologies. So before we actually go out into the field, we want to test a lot of these technologies, a lot of our algorithms inside of a simulation environment. This enables us to both improve our software, and we can also get a sense of what is the potential benefits from a particular technology. So the traffic simulator itself, we need something that is able to produce real-world traffic scenarios. We would like to have streets that we can drive on in a simulated environment that we can control to some extent, but that also respond in a very realistic fashion, because we want to be able to test in, like I said, a very realistic environment. We want to also enable the calibration and testing in a controlled environment, but one that we can also modify and change to better suit our needs. This is a summary of the necessary functions of the traffic simulator. First and foremost, we want to be able to control 5 ego vehicles. So this is an external control which would allow us to control the vehicles inside of the simulation and enable us to perform the eco-driving maneuvers that Sankar has previously discussed. We next also want to inject 50 other vehicles. We're certainly going to be experimenting with a lot more, but we want to have the interactions of our vehicle, our connected vehicles, with other vehicles inside of the simulation. We want those vehicles to dynamically react to our ego vehicles in order to more realistically represent this environment. Next is data logging. We want to be able to log all of the vehicles simultaneously. This will enable us to perform energy calculations offline for all of the vehicles, not just the ego vehicles that we are controlling. Next is simulation stability. The simulation needs to be deterministic. It needs to be real time, because our solvers operate in real time. We collect information, we process it, and then we give the output, the command, to the vehicle speed. And finally, of course, our V2X capabilities. So speed, location, and information of other vehicles needs to be communicated to our ego vehicles. We should then be able to use that information and, in turn, better inform our ego vehicle of the upcoming events. And this does include traffic signal, phase, and timing information as well. Again, it's just more information for us to better dictate what our speeds should be. So here's an example of what we are really looking for producing in a traffic simulated environment. At the bottom, you will see a screenshot of Google Maps. It is taken from an origin destination. This was an actual route that we have driven, but we have also collected a lot of information about the traffic patterns from state DOTs. And at a high level, we can of course go to Google Maps and plot out the velocities, the average speeds of this route. And as you can see, there are some areas that are experiencing high traffic areas, and so you'll have a smaller overall average speed. And in some areas you have free-flowing traffic. We want a simulator that can not just replicate realistic traffic, but also realistic environments. That is to say, we want to, if we were to create this environment inside of the simulation, we want it to have some of these characteristics of slower traffic in some areas, some specific areas that are reflective of the real world. So this is where Vissim comes in. We did an evaluation of Vissim, and we saw that it offers some flexibility with what we can do. It offers MATLAB and C++ integration. We of course have options of interfacing it with it in a manner of in other manners as well. We have flexibility in terms of placement and control of vehicles, which allows us to both inject vehicles where we want to. It will allow us to create more realistic traffic flows, traffic counts. And we can also query any environment features, so roads and traffic lights, as well as other vehicles as well. This kind of brings back to the connectivity of things. So we knew that some development effort would be needed to align the tool with our application, specifically things like V2X. We needed to provide a different way of accessing those resources and providing that information to our eco speed solvers. So with Vissim, we're allowed to externally control certain parameters in some vehicles, which we needed to integrate with our NEXTCAR speed optimizer. We needed to do this in a real-time fashion, and so we use the COM interface with MATLAB. Our NEXTCAR speed optimizer is currently written in Simulink, and so integrating Vissim with MATLAB allowed us a fairly quick way of getting to this achievement. So we're able to send ego vehicle information to the Simulink optimizer. The optimizer solves for the speed, and the speed command is then issued to the ego vehicle or ego vehicles inside of Vissim. Next, we'll look at specifically the Vissim control. So if you look at the overall process, what we're doing with the ego vehicles is first we create a new vehicle type and class. Next, we create a route between a specified origin and destination. And once that is done, then we add the vehicle to the simulator. The graph on the right shows the process once we have added the vehicle to the sim, starting with the V2X information. First, we query all of the information about the environment. We perform lane and link filtering because the V2X information is going to be around a radius, and we need to specifically filter out all the cars that are traveling on other roadways or are traveling in a different direction. We only really care about the vehicles that are in front of us. Next, we look at the signal heads. We query all of the features on our path, and we figure out where are the signals and what are the timing information that is associated with those signals. That information is fed into the speed optimizer, which gives us the target velocity that our vehicle should be traveling. We then command that target speed from our simulator back into Vissim, and the vehicle in Vissim will, of course, our ego vehicle in Vissim will drive that commanded speed. We log all of this information, and then we go into the next step of the simulation. So we're currently running between 10 and 20 hertz. So this the size of that step will vary accordingly. So first, maybe in a little bit more detail, we create the ego vehicle. In order to do that, we create a unique vehicle class and type. Then we also add a vehicle routing decision, a static routing decision. This allows us to control just our vehicle, and other vehicles will not follow necessarily our routing decision. We launch the simulation in single-step mode. This gives us the ability to query features within Vissim in between steps, and then we can add the vehicle at the desired position. Next comes the important part of V2X information. We need to request the information from nearby vehicles and as well as from the infrastructure. So we do that by getting attributes by location. If you have an object in Vissim, a vehicle object, you can go in and ask for attributes by location. This gives you the information the attribute information of all the present vehicles in a surrounding radius. We then find the route link sequence for our ego vehicle. We see what is the route that we are going to follow. And this allows us to filter down the vehicles in this radius to just those that are going to be in our path. Because we know that in the simulated environment, we will have many different links and lanes, and all of these are somehow interconnected, and the route link sequence is something that connects it to us, to our vehicle. Next, we'll look at the upcoming signal heads. We query the features, and this includes a couple of custom attributes that allow us to look at the remaining time in a particular phase. So as the vehicle is approaching that light, we both get the phase as well as the remaining time in that particular phase. And finally, we look at the desired speed decisions. Anytime our vehicle approaches or passes a desired speed decision, we update that accordingly in the solver because it gives us a target speed that the ego vehicle should be traveling. Now at the bottom, you will see a screenshot that shows the type of information that we're looking for. So imagine you are in the ego vehicle, and this is what you'll be looking at. So you can see that there are some vehicles. So these are the vehicles that are present in front of us. You can see that the distance that those vehicles are present, and then as well as some other more relevant information such as their speed. We can use the speed of the vehicles in front of us to more accurately decide which speed we should be traveling. Because if we know that this vehicle is stopped and it's fairly close to us, even though this vehicle is still traveling at some speed, we don't need to also try to follow it. We can begin to slow down knowing that the vehicle ahead is stopped. So then we actually command the ego vehicle speed. Now that we've parsed all the information for each ego vehicle and passed it to the optimizer, we set the vehicle speed from our Simulink environment back into Vissim. We save all the vehicle positions as well as some of the attributes to a log file, and we advance the simulation step. Now, I will come back to this as well. We are saving the vehicle positions of all vehicles in the simulation, because coming back to what we're trying to do here, we're trying to see whether our ego vehicles can, one, benefit themselves, but two, how do they affect the environment around them? We care about the throughput of a particular roadway. If our vehicles act in such a way as to slow down other traffic, that is a big negative. But do our vehicles also affect the other vehicles in the simulation in a positive way? Are we actually perhaps providing some of that speed smoothing that you saw in the initial video? This is the control panel that we're using in Simulink. It is fairly basic, but it allows us to add ego vehicles whenever we want to. You'll see at the top here, these are the origin destinations that we can set. Once we add the ego vehicle, we have these control panels that show us in real time what our vehicle is doing. So this is the speed that we're traveling. and then this is the information about the lead vehicles in front of us. So we can see that there is a vehicle in front of us at 41 meters. There's another vehicle beyond that at 86 meters. They're both traveling at 8 kilometers an hour. Next, we also have information about traffic lights. This includes information about the distance to that traffic light, its state. This is an enumeration, and then we also have the time remaining in that particular phase. We'll start and stop the simulation as well. And of course, the simulation can be run without adding any ego vehicles, in which case traffic will continue to flow as it would by default. In a little bit more detail, this is the eco-driving control. And to summarize, in a more perhaps simpler fashion, we acquire the V2V and V2I data. The ego vehicles are controlled via an external command, that is to say, our solver. The performance needs to be 10 Hertz or better, because we are doing this in real time. And we need to have the lane level identification and filtering of vehicles. You will see right here, for example, that we are in this yellow vehicle. As we are approaching this intersection, on the left, you will see that we see 4 vehicles in front of us, as well as the traffic light, its distance, its state, and its time remaining. All of this information will feed back into our solver, which allows us to more accurately give a good speed decision. And then we're going to look at the post-processing framework. So remember, I said that we log not just our vehicles, but all of the vehicles in the simulation. What do we do with that information? On the left, you'll see the traffic simulation software. This is what gets us all of the data about the vehicles in this environment. That information is then fed into a number of scripts. These include the GT models. These include Simulink models. And these are models of different vehicle powertrains. This information is then able to be summarized in a visual fashion, where we can take any of the vehicles from the simulation, we can assign it a particular powertrain, and then we can determine how much energy was expended by that vehicle. Now, one of the important things to note is the powertrain mix of traffic can be tuned in order to understand the impact on energy consumption. Because, of course, ICE, internal combustion engines, are going to perform much different than a plug-in hybrid. And we've also seen studies that show that predict that up to 35% of vehicles will be hybrid electric or plug-in hybrid electric vehicles in the market. And so how does a different powertrain mix in the future affect the overall energy consumption, and how can we impact that as well? More specifically for our program, this is the simulation corridor that we're looking at. This is a corridor in Columbus, Ohio. It is 3.7 miles long. It has 27 major signalized intersections. It starts from the south portion of the central business district and goes up north along this high street, which terminates at approximately the end of the Ohio State campus. The reason we chose this is because one of our partners, Continental, operates a smart intersection stack at this intersection on Goodale Street. What this intersection stack provides us is vision and radar systems to track other vehicles. Now, in the real world, we have very limited information about connected vehicles. Simply, connected vehicles are not as prevalent, prevalent in the current market. This smart intersection stack will actually enable us to bring in non-connected players into our environment. Doing the evaluation along this corridor initially will allow us to test our systems in a simulated environment, and then we can actually bring our vehicles, bring our systems into this real world and compare how our results match up. Now, if we look at the energy benefits behind eco-driving, One of the things that we've done in the past, this was with the NEXTCAR program, is we had a traffic simulator that was integrated directly with a vehicle on a hub dynamometer. As the vehicle is driven as the vehicle is being driven by a human on the dyno, that speed is communicated in real time to the traffic simulator. That vehicle, of course, will move in that environment and provide, and its environment, of course, will change in real time. The driver of the vehicle on the dyno can, in turn, see the changes in the simulated environment and react accordingly, just as they would driving in a realistic environment as well. And this is where Vissim is another tool that can help us greatly, because it has some nice 3D capabilities, and some of the images that I've shown in some of the previous slides showcase some of that capability, where we can have a driver who's sitting with a screen inside of the simulated environment, responding to the environment in a realistic fashion, and we're tracking all that information on a vehicle and hub dynamometer. This gives us the ability of quantifying any energy benefits of our route. And this is a summary of some of the benefits of a vehicle that we've tested on a dyno. What you're seeing here is a bivariate distribution. The lines in the orange are the probabilities that using a collection of simulated drives, we're able to plot out the energy consumption as well as the trip time for those particular routes. So this is going to be, the orange lines are going to be so these different data points are going to be our eco driving vehicle, and then the black symbols are going to be the routes that were taken by default by the default simulated software. So you can see a shift in the mean towards the left, which means that the eco driving vehicles are actually using less energy to traverse the same route, and even a shift in the downwards direction, which is trip time, showing that we have a slight advantage also in the amount of time that it takes for vehicles to travel through this corridor. Now, this is very, very positive news for us, because it shows that indeed the eco driving software does have quite a bit of merit to it, because we're seeing a very significant 10% energy improvement per vehicle on dyno, just using this particular speed control and using this particular traffic environment. So in summary, as the connected powertrain, as part of the purpose of the connected powertrain is, we're evaluating system-wide improvements using things like intelligent infrastructure. We're evaluating diverse powertrains as well as various automation levels. In order to evaluate this, we are performing controlled calibration and testing. For that, we're using the connected simulated environment in environments like Vissim. We are able to externally control vehicles from these simulated environments, and then we are operating our connected automated vehicle dynamometer in order to give us numerical quantity behind the numbers that we're seeing in the simulated environment. That is all that we have for the presentation. If you have any questions, please enter them into the chat window, and we will answer them closer to the end of the presentation. This is our contact information. If you have any questions, please feel free to reach out.